Welcome back. In this session we will look at the implementation of genetic algorithm. So, we will be directly implementing real coded genetic algorithm. So, for that we will be using the SBX crossover operator which we have discussed, and for mutation we will be using the polynomial mutation that we have discussed. Right. So, before actually implementing genetic algorithm, let us quickly have a recap of the pseudocode of genetic algorithms that will help us to quickly implement the algorithm. Right. Pseudocode, as we have seen, we need to provide the fitness function so that the objective function can be evaluated, the lower and upper bound. So, these three constitute the details about the problem. We need to give the population size, the number of generations we want to carry out, because that would be our termination criteria, the mutation and crossover probability indicated by PCPM, and for SBX crossover we required distribution index for crossover, and eta m indicates the distribution index required for the polynomial mutation, and k is going to be the number of candidates involved in the tournament. So, in our case we will take k is equal to 2. So, the code which we have written is on the assumption that k is equal to 2. So, we will have competition between two solutions and the winner will get into the mating pool, right. So, in our case for the code which we are going to discuss, k is fixed to be 2. So, the first step is to initialize a random population within the lower and upper bounds, and then we need to evaluate the fitness of the population. Right. Once we have done this, we have this iteration loop, exterior iteration loop. The steps given in this loop will have to be performed capital T times, right. So, for every iteration we need to do a tournament selection, right. So, in each tournament the number of candidates competing will be k. So, in our case it is going to be 2. So, based on this tournament selection we will select NP population members, right. Once we are done with that, in this for loop we will be implementing the crossover operator. So, since there are NP solutions and we require 2 members per crossover, the number of crossovers would be 1 to NP by 2, right. So, again because of this criteria, NP has to be a even number. So, in this case we will randomly choose 2 parents, we will generate a random number. If that is less than equal to crossover probability, we will perform crossover, else we will directly copy the selected parents and their fitness to offspring population. Right. If we happen to do crossover, then we will be using this SBX crossover which is given over here. Right. So, for each variable we will have to generate a random number between 0 and 1, depending upon whether it is less than equal to 0.5 or greater than 0.5, we will have to calculate the beta value, and using the beta value we need to calculate the offspring 1 and the offspring 2. Okay. So, that is going to be the crossover. So, once crossover is performed, we need to do mutation for each of the NP members, right, on the offspring. So, at the end of crossover we will have offsprings. So, we will be performing mutation on the offsprings, right. So, again we will have to generate a random number. If that is less than equal to mutation probability, we will be performing the polynomial mutation, else we will not change the solution. And then once we complete mutation for all the NP members, we will evaluate the fitness of all of them and then combine the parent and offspring population to select the best NP members. So, we will be employing a mu plus lambda strategy. Mu is our parents, lambda indicates the offsprings which were generated. So, we will combine all the solutions which we have, mu plus lambda, and we will select the best NP members. This is the pseudocode of real coded genetic algorithm, right. So, let us see its implementation. So, let us first quickly go through the code and then we will execute it line by line. So, these two statements are to just clear the command window and the workspace. This statement line 4 ensures that we get the same set of random numbers every time we execute this code, right. So, we are using the RNG inbuilt function of MATLAB, right. We have to use this RNG function, we need to provide a seed and an algorithm. So, there are various algorithms to select the random number. We have chosen the twister algorithm and we have set the seed to be 2. So, every time we run this algorithm we will get the same values as long as we do not change this, right, despite the fact that it is a stochastic algorithm. This RNG ensures that we get the same set of random numbers every time we execute it. So, these three things are straightforward. We are defining the lower bound of the problem, upper bound of the problem, and we are defining the function sphere new, right, into the variable prob. So these are the 6 parameters that are required for executing GA. One is the population size, the number of iterations, the distribution index for crossover, the distribution index for mutation, the crossover probability and the mutation probability. So our results are sensitive to these values which we have taken, right. So these values have to be provided. So we are not providing k over here, because the code itself is built for k is equal to 2. As you will see, when we are writing the tournament selection function, we will be comparing only 2 solutions. So that is inherently fixed in this code. So then we define some of the variables which will be required, right. So again, as usual, we define f, right. So f is to contain the fitness function values of the NP population members. Initially we are initializing it with NaN, right. As and when we calculate, we will assign the appropriate value, right. This offspring obj will contain the fitness function value of the offsprings. From the parents we will generate offsprings, we will evaluate its fitness function value. So those would be stored in this variable offspring, right, obj. So again, the size of offspring will be the same as the number of population members. So the number of decision variables of the problem can be calculated by determining the length of lower bound, right. So lower bound in this case is 2, so d would take a value of 2. So as and when we change the number of elements in the lower bound, d would automatically get evaluated and subsequently it will impact the rest of the program, right. So line 29 is the generation of the initial population, right. So we are replicating the lower bound NP times, plus we are determining the range, right, that is the range is UB minus LB, we are replicating that NP times, right. So this second part, this highlighted part will have a dimension of NP cross D, right. Similarly, we are generating NP cross D random numbers between 0 to 1, and then we are doing a element to element multiplication, right. So this line will help us to determine the population. At the end of line 29, we would have generated the population members. So 31 to 33 in this for loop, we are determining the fitness function value for each member, right. So this loop runs for NP times, right, and each time we are sending the pth row. So this p of p comma full colon will ensure that we are sending the entire pth row. We are sending it to the function handle prob. Function handle prob is nothing but spear new or whatever function we define, right. So that way we will be evaluating the fitness of each member, right. So line 31 to 33 will help us to evaluate the fitness of the randomly generated population. Once that fitness is evaluated, we are ready to begin the genetic algorithm, right. So this is the iteration loop, line 36 to 58, whatever is there in between line 36 to 58 will be implemented capital T times, because we want to perform T iterations, right, which is a user defined parameter. So genetic algorithm, if you see broadly, there are 3 operations that we need to perform. One is the tournament selection, right. From the tournament selection we will get the mating pool. This mating pool will have to be used for crossover, right, and mutation. So first we will perform tournament selection, we will select the mating pool. This mating pool will be used for crossover and we will generate offspring. Those offsprings will be used for mutation. So we will use 3 function files, right. Tournament selection we are going to implement in a separate function file, crossover SBX crossover we will be implementing in another function file, and polynomial mutation we will be implementing in another function file, right. So and we will be just accessing those 3 files. So here if we see, so the 3 functions are tournament selection, crossover and mutation poly. So from tournament selection we will get the index of the population members which will constitute the mating pool, right, and then we are accessing those members, right. So mating pool will be not a set of solution, but it will merely indicate the index of the solution, right. So since we know the index, we are accessing those population members and we are giving it to the variable parent, right. So once this parent is fed into this crossover SBX operator, right, we will get the offspring. This offspring is in turn fed into the mutation poly function, which is nothing but polynomial mutation, right, and then we will get the final offspring, right. So for the final offspring we will evaluate the objective function, right. The number of offsprings will be equal to the population size, right, and then we will be combining the population, right. So this is the initial population P, we are combining with offspring, right, and that will be the combined population. Similarly, we are combining the objective function like stacking one below the other, right, and then we are sorting, right. Once we sort, we will get f, and we will also get a track of which variable which value has been sent to which position, right. So, that will be stored in this IND. So, once we have this f and IND, so we are in need of only NP population member. So, the size of f will be 2 NP, size of int will be 2 NP, right, but we require only the first NP values, right. So, what we will do is we will say f, which is for the subsequent generation, only the first NP values. We are extracting the first NP values and storing it in f. Similarly, p is nothing but the combined population which we have determined over here, right, and then we are accessing only the first NP elements of int, right. So, int will have the indexes which are on the top. So, we are selecting the first NP solutions, right, first NP solutions indicated by this variable IND. So, we are extracting those solutions, right, and then we are storing it in the variable p, right. So, this is what is going to happen. So, now let us look into the tournament selection operator. The input to this tournament selection is the fitness function value of the NP members and the size of the population NP, right. So, only those two things are to be fed. We do not need to decide which are the solutions, because if you remember, when we formed the mating pool, we were only determining which solution is better, right. We were not looking at the decision vector, right. We are only looking at the fitness function value. So, that is why we are sending only the fitness function value over here, right. So, let us look into this tournament selection, right. In tournament selection, what we receive from the main script is the fitness function value and the size of the population, right. Here we have explicitly given the size of the population, otherwise that can also be determined using the length of f, right. So, this tournament selection operator ensures that each solution gets to participate in 2 tournaments, right. So, that is how we had looked at the tournament selection. We are implementing a binary tournament selection, where in each tournament there are 2 solutions, and each solution in the population will get 2 opportunities. So, initially we are defining this mating pool as none with a size of NP, right. So, we are ultimately going to store in this mating pool as to which of the solutions, not exactly the solutions, their locations, right, which of the solutions would constitute the mating pool, right. So, that is what is going to be in this mating pool. In this line, we are using the ranpom function. Let us assume that NP is equal to, let us say 6, right. So, what we will do is we will first shuffle the number 1 to 6, right. So, the numbers which we have is 1, 2, 3, 4, 5 and 6, right. So, we will use this ranpom function in MATLAB when we do ranpom of NP, right. So, it will help us to shuffle these numbers. So, let us say that the shuffled numbers are 6, 3, 4, 2, 1, 5. So, all the numbers would occur once 1, 2, 3, 4, 5, 6, right. So, this is what we will be indicating by the variable INDX, right. Since our population size is 6, we need to conduct 6 competitions, right. So, how we are going to conduct the competition is the 2 neighbors are going to compete, right. So, the first competition is going to be between solution 6 and solution 3, right, these 2. The second competition is going to be between solution 3 and solution 4, right. So, that would be this competition. The third competition would be between solution 4 and solution 2. This is the third competition. Fourth competition is going to be between solution 2 and solution 1, right. Fifth competition is going to be between solution 1 and solution 5, right. Now, to conduct the sixth competition, right, we have solution 5. All the other members except 6 and 5 have already participated twice. So, for example, S3 has participated twice, S4 has participated twice, S2 also has participated twice, S1 also has participated twice, right. So, only S5 and S6 have participated once, right. So, that is because the 6 is located over at the top. So, the last competition is going to be conducted between the last value of this index and the first value of this index, right. So, that would be between S5 and S6. This is the way we are going to conduct NP tournaments, right. So, from each tournament we will get one solution. So, at the end of it we will get NP solutions, and every solution would have got an opportunity to compete twice. So, with this, let us say this S5 has also got twice, S6 also has got 2 opportunities, right. So, this is how we are going to implement the tournament selection, right. So, when we are implementing this tournament selection, right, so we will obviously be running a loop from I is equal to 1 to NP, and the members would be, so members we will call it as candidates, right. So, the candidates would be I and I plus 1, right. So, the first time when we do I and I plus 1, 1 2 will be fine. The second time when I is equal to 2 3 would be fine, right, and similarly for all the variable will happen, and then when I is equal to NP, right, we will have a problem because we are trying to access the NP solution and NP plus 1 solution, which we do not have, right. So, that is why we will run this loop for I is equal to 1 to NP minus 1, right. So, we will be conducting till this 5 competitions, and this competition we will be conducting separately out of this for loop, right. Whatever happens in the for loop, that is there, and out of this for loop we will conduct one more competition. That competition will be for the last member in this index and the first member in this index. So, that competition will be conducted separately, right. So, this INDX will shuffle the solutions and give them in a random order, right, of the NP solutions which we have, right. So, what we are doing is we are running 1 to NP minus 1 times. Our population size is NP, so our pool size is also to be NP. So, in this case what we are doing is, first we are selecting NP minus 1 solutions, then what we are saying is we are selecting the candidates who will compete, right. So, this ensures that there are NP minus 1 tournaments, right. So, from each tournament we will get one winner, right. So, when this loop is completed, 7 to 12 is completed, we will have selected NP minus 1 solutions. We are supposed to select NP solutions, but right now we are selecting only NP minus 1 solutions, right. So, what we are doing here is we are selecting the ith value and the I plus 1th value. So, that is what I had indicated to you, that the first and second 2 subsequent solutions would be participating in a particular tournament, right. So, we are taking the 2 neighbors. So, the neighbor is I and I plus 1. So, these are the indexes of those are put in candidate, and then over here in line 9 we are accessing their objective function values or the fitness function values. So, now we know the 2 solutions which are participating and their fitness function value, right. So, the fitness function value is stored in candidate obj, the indexes of the solution are stored in candidate, right. So, now since we need to work with this fitness function value, we are finding out which is the minimum of 2. So, this candidate obj, its value will always be 2 cross 1, 2 rows 1 column, because we have selected 2 candidates. We are determining the minimum value in it, right, and we are not interested in the value as such, right, we are only interested in the winner. So, the winner would be indicated by the position IND, right, and then we access that particular candidate and put it inside the mating pool, right. So, mating pool of I is going to be the winner candidate. This we will be able to see with an example, right. Once we get into the debug mode and when we execute it, this part of the code will be much clearer. So, so far we have selected NP minus 1 solutions. So, here what we are doing is we are selecting the candidate index of NP, right. Index of NP would be the last value in this variable index, right, and the first value. We are now selecting these 2 solutions. So, that is candidate. So, it will store the index. Once we store the objective function values of those 2 candidates in this candidate obj, we can find out where is the minimum located, right. So, depending upon where this minimum is located, using this variable IND, we access that particular candidate and we dump it into the mating pool, right. So, this is the tournament selection which is implemented. So, it is a binary tournament, every member will be able to participate exactly twice using this code. So, that is why k is not given as a user defined parameter. Inherently we have assumed k to be 2 when we wrote this piece of code. So, that completes our discussion on tournament selection. Obviously, for some of you it would be still little bit problematic to understand, but once we run this code, we will be able to actually see what is happening. It is similar to that example that we used to solve. Once you solve an example, things become a lot more easier to understand. So, the same thing over here, once we execute this code with a sample problem, you will be able to better understand this tournament selection. So let us go back to the genetic algorithm script, right. So from the tournament selection we obtain the mating pools. This function will provide the mating pool. When we say mating pool, it will be just a vector containing integers, right. So let us say if the vector contains values 2, 4, 8, 9, it means the second solution, the fourth solution, the eighth solution, the ninth solution comprise the mating pool, right. The entire solution vector would not be there, but only their location or their indexes would be available in the mating pool. So once we know the indexes, we can actually extract the entire solution using the population, right. So that is what we will be doing over here. So in this line 40, that is what we are doing, right. So parent is equal to P of mating pool, right. So those particular rows and their corresponding columns, all the columns corresponding to that selected rows, right. So mating pool will be a vector. So let us say mating pool is 2, 4, 8. So what we are doing is this entire second row, the entire fourth row and the entire eighth row is selected and stored in this variable parent. So that is the reproduction operator. In the reproduction operator or the selection operator, we have determined the mating pool, the solutions which are reasonably good, right, which can go for crossover. So coming to this SBX crossover operator, so there we will have to pass on the values of the parent, right. We will have to give the crossover probability, whether crossover needs to happen for a particular pair or not, that would be determined by the crossover probability. This eta c is the crossover index which will be required in the equation for SBX operator, and the lower bound and the upper bound, right. So there is no guarantee that the solutions which are generated by SBX crossover operator will be within the bounds, right. So if it is out of the bound, we will have to bound it, right. So to bound this, we are actually passing this lower bound and upper bound, right, and what we are expecting is the offspring from crossover operator. So let us look into this crossover SBX. Before actually looking into this crossover SBX, let us quickly recap SBX crossover. So for SBX crossover, first we will have to select two solutions and then we will have to decide whether they are going to go for crossover or not. That will be decided by a random number which we select. A random number, if we say it is 0.2, and if our crossover probability is 0.8, so 0.2 is less than 0.8, so that particular pair will undergo crossover, right. So if that particular pair comes for crossover, what we will have to do is we will have to first generate U. U is a random number between 0 and 1. So for each variable we will have a random number. So if we have d decision variables, we will have to generate d random numbers between 0 to 1, and for each of them we will have to check this condition, whether random number is less than equal to 0.5 or greater than 0.5, right. Depending upon that value, we will have to calculate beta. Since U has to be selected for each variable, we will have a beta value for each variable. Once we calculate beta value, then we know the parents, right. So once the beta values are known, using the two parents x1 and x2, or let us say p1 a and p prime a and p prime b, right. So x1 and x2, you might be confusing it with the decision variables. So to distinguish that, we can use p prime a and p prime b. So these are the two parents which are undergoing crossover, right. So once we know beta, we can use these two equations to generate two new offsprings, right. So this is how we will be generating two offsprings using SBX crossover, right. And if the random number which we selected happens to be greater than crossover probability, then we will merely copy the parents as the offsprings, right. Then there is no crossover operator, but the parents are copied as the offsprings, right. So for this SBX crossover operator, we will have to provide the parent, right, the crossover probability, the distribution index eta c, the lower and upper bound, right. So first what we do is we determine as to how many members are there and what is the size of the problem or how many decision variables are there. So size of parent gives the number of rows and number of columns. The number of rows will indicate the population size and the number of columns would indicate the number of decision variables, right. So again we will be using this ranpum function, right. So ranpum function, as we have seen previously, will help us to shuffle the numbers from 1 to np, right. So we will shuffle the numbers. So this will only give the location, right, and then what we are doing is we are arranging the parents, right, as per this index which we have obtained in this line 4. So in line 4 we will merely get the indexes. Now this parent is randomly shuffled, right. This we are doing because at the end of a particular iteration we will be sorting, right. So, since we are sorting the population, the good solutions will be at the top, right, whereas when we are doing crossover we are supposed to randomly select, right. So, what we are going to do is we are going to select the first solution, second solution, and since the fitness function are sorted, we will be pairing two good solutions. So, we want to avoid that. So, that is why we are using this ranpum function to shuffle the solutions, right. Once the solutions are shuffled, it might happen that the first solution is good, the second solution need not be the second best solution, right. So, that way it will help us to create a diverse population, right. So, we create this parent population and then we will be using this variable offspring to store the offsprings which we generate, right. So, the size of this is known a priori, that there will be NP rows because there are NP parents, and there will be D columns because the number of columns in offspring will be equal to the number of decision variables, right. So, this is just we are pre-allocating the memory. So, once that is done, we are going to implement the crossover, right. So, for crossover we are implementing this loop. So, this for loop we are implementing from 1 in interval of 2 to NP, right. So, first time the value of I will be 1, second time the value of I would be 3, the third time the value of I would be 5, right. So, it will jump in steps of 2, 1, 3 and 5 and so on till we get this NP, right. So, that we are doing because we will be taking the first solution and second solution. So, second time when we are doing crossover we will be taking the third solution and the fourth solution. When the third time we are implementing crossover we will be selecting the fifth solution and the sixth solution, right. So, that is why we skip in intervals of 2. So, first thing is to decide whether we need to perform crossover or not for a particular pair. We generate a random number using this ran function, the value would be stored in R, and then we check over here whether R is less than PC, right. If R is less than PC, then we need to perform a crossover which will be happening in this section from line 14 to line 26, right. In this section crossover would be happening. So, to perform the crossover we have D variables, right. So, here we have chosen to implement it through a for loop, so that it is easier to understand for those of you who are not very comfortable working with vectorized code, but this could have been vectorized, right. So, what we will be doing here is first we will say j is equal to 1, we will generate a random number, right. If that random number is less than or equal to 0.5, then we will use this equation to calculate the value of beta, else we will use this equation to calculate this value of beta. So, remember there were two equations for generating the value of beta. So, depending upon the value of random numbers we had to select one of those equation, right. So, this R was to decide whether we need to perform crossover or not. This R helps us to determine which of those two equations would be used to find out the value of beta, right. So, once we have generated the value of beta, we can find out the two offspring, right. So, the jth variable of the ith offspring would be 0.5 into 1 plus beta. So, beta would be a scalar value, right, 1 plus beta into parent of I comma j. So, the ith parent, right, plus 1 minus beta into parent of I plus 1. So, the second parent. So, first time when we are doing I will be 1. So, parent of 1 comma 1 plus 1 minus beta into parent of 2 comma 1. So, the first variable of the second parent, right. So, similarly we generate the second offspring, just that instead of this plus we have a minus over here, and instead of this minus we have a plus over here. So, that is how our two equations were, right. So, this will help us to generate the two offsprings, right. So, once we have generated the offsprings we need to make sure that they are bounded. So, here we check for the bounds. So, this for loop is completed for all the D variables. Once this is completed, we check for the newly generated solution. So, the newly generated solution is the ith solution and the I plus 1 solution. So, we check whether it is in the lower bound and the upper bound, whether it is in between lower and upper bound. If not, we employ the usual corner bounding strategy to bound it, right. So, this is the condition if we decide to perform crossover, right. But if we decide not to perform the crossover because of this randomly generated number, right, then we will directly copy the parent, and since parent is copied we do not have a bounding procedure over there. So, with this we will be able to generate NP offsprings, right. Why NP offsprings? This loop does not run for NP times, but each time the loop runs we generate 2 offspring, and the loop will run for np by 2 times, and each time we will get 2 offspring. So, at the end of the completion of SBX crossover operator for all the solutions, right, we will have NP solutions which are known as offspring. So, here one thing that you need to remember is that we are generating 2 offsprings, right. So, offspring I as well as offspring I plus 1. So, both of them need to be bounded. So, here if you see in line 28, 29, what we are doing is we are bounding for both the solution, the ith offspring and the I plus 1th offspring, we are checking for the lower bound, right. So, the offspring is indicated by offspring I comma colon. So, this the highlighted portion indicates the offspring, this is the lower bound, and we are using the max operator. So, what we will get over here in line 28 is that the ith offspring no longer violates the lower bound after this line is executed. Similarly, this line 29 is for making sure that the I plus 1th offspring does not violate the lower bound, right. So, both of these lines only take care about the lower bound, and similarly both of these lines line 30 and line 31 take care about the upper bound, right. So, the ith offspring we are using the min function to make sure that it does not violate the upper bound, and similarly in line 31 we are bounding the I plus 1th offspring with the upper bound. So, this you need to make sure that both the solutions do not violate the upper and lower bound, right. So, that is why we have 4 lines over here. Once we have calculated the offspring, right, we need to go back, then we need to perform the polynomial mutation. So, again we will be providing this offspring to the polynomial mutation function. So, here we have used the function mutation poly, right. So, mutation is done using polynomial mutation, that is why it is mutation poly. We need to give the offspring which were generated from crossover, we need to provide the mutation probability, we need to give the distribution index for mutation, right, and the lower bound and the upper bound similar to our crossover, because in mutation also it is not guaranteed that the solution would be between upper and lower bounds, right. So, if it is out of bounds we will have to bound it, right. So, now let us look into this polynomial mutation function. So, this is our function, right. So, before looking into the function we can quickly recap polynomial mutation, right. So, again similar to crossover we will have to generate a random number. If the random number is less than or equal to mutation probability Pm, this is user defined value. So, if this relation satisfies we will perform mutation, else we will not perform mutation, right. So, if we do not perform mutation, the offspring which we generated from crossover will remain the same, right. So, this is the condition that we will have to check. If this condition is satisfied, right, then what we will have to do is we will have to determine, we will have to generate d random numbers, right. So, because we have d decision variable. So, for each of that we need to go and check whether r is less than 0.5 or r is greater than or equal to 0.5. So, if r is less than 0.5 we will use this equation to determine the value of delta. If r is greater than or equal to 0.5 we will use this equation to determine the value of delta, right. So, once we determine the value of delta we can generate the new offspring using this equation. So, the current offspring for which we are doing mutation plus ub minus lb. So, these are the lower and upper bounds of the problem into del which we have calculated here, right. So, this will give us the new offspring which is called as y over here, or you can just call it as o, right. So, this will be our new offspring. So, we will receive the offsprings, the mutation probability, the probability index for mutation eta m, the lower and upper bound. So, similar to crossover we first determine the number of population and the dimension of the problem. For each solution we will be performing mutation. We generate a random number r. If r is less than the mutation probability we will be performing the mutation, right, else we do not need to do anything, right, the offspring will be remain the same, right. So, if it happens that we need to perform mutation, then we have to run a loop for j is equal to 1 to d for all the d decision variables. So, we again generate a random number r is equal to rand, and if the random number which we generated happens to be less than 0.5 we determine the delta by this particular equation, else we determine the delta by this particular equation, and then we say the new offspring is the current offspring, right, plus upper bound minus lower bound into delta. So since this we are doing it variable by variable, that is why we are having offspring, the jth variable of the ith offspring is equal to the current jth variable of the ith offspring plus the upper bound of the jth variable minus the lower bound of the jth variable into delta. We are not saying delta of jth variable because delta we are individually calculating for every decision variable, right. So that is going to be just a scalar, right. So we directly multiply it with delta. Once this for loop is over, we would have completed mutation, right. So again here we are merely bounding it, right. So the ith member, if it is violating the lower bound, we use the max operator, right, to bound it to the lower bound. If it is violating the upper bound, we use this min operator to bound it to the upper bound. So this is the polynomial mutation function. So it's very easy to implement. There are only 4 or 5 steps, right. First is to generate a random number, check it with mutation probability. Second is to, if mutation has to happen, we need to generate random numbers for every decision variable, and depending upon the value of the decision variable, we will have to use one of those equations to calculate the value of delta, right. After determining the value of delta, we will have to generate the new offspring, which is the current offspring which is undergoing mutation plus upper bound minus lower bound, which are the domains of the decision variable, into the delta value which we calculated, right. So this has to be implemented for all the solutions. So let us go back to this. So once we have implemented polynomial mutation, again we will get the mutated offsprings, right. So this step is very straightforward, that each of the offspring is being sent to the objective function using the function handle prop, right, and we will be able to determine its fitness function, which is stored in the jth location of this variable offspring obj, right. So now at the end of line 50, when we have completed this for loop, we have NP parents and NP offsprings, right. So that we are combining, right. Combined population is P semicolon offspring, right. So that is the combined population. So now we have combined only the decision variables, right. So the size of combined population would be 2 NP rows, right. So if our population size is 6, then we will have 12 rows by the number of decision variables. So if we have 10 decision variables, it will be 12 cross 10 if NP is 6, right. So the combined population only takes care of the solution. The fitness function is actually stored in F and this offspring obj. So we need to stack them and then we are sorting, right. So once we sort that, we will get the sorted fitness function value and we will also get this index variable. So this index variable helps to identify as to which solution has gone into which position, right. So using this IND variable, we will be able to extract the best NP population, right. So ind of 1 to NP corresponds to the population for which the fitness is f of f1 to NP, right. So that is how we extract the population from the combined population and the fitness from the combined fitness function value. That completes the implementation of genetic algorithm. So these two lines are similar to what we have been implementing in other algorithms, right. We find the minimum value of f, right. So that you get the best fitness function value and its location, and then we extract the solution using this IND variable, right. So here we have shown it, but the better way of doing it is directly accessing it from f, right. So f is already sorted. So obviously since it is sorted, the first value corresponds to the minimum value and the first value of the variable p will correspond to the best solution, right. So it is not necessary to once again find out the minimum and then call it to be the best fitness function value. Now let us execute this program. So let us get into this debug mode, right, and we will execute it line by line. So let me just give this run. So the first 2 lines you are familiar with it, it will clear the screen and clear the workspace, right. So this will fix us the set of random numbers that will be used in this code, right. So that is straightforward. So these next 3 lines are defining the lower bound, upper bound and problem, which is common for all the other 4 techniques which we have seen. So these 6 lines will help us to fix the parameters required for executing genetic algorithm, right. So then we are defining a variable f, right, which will have nan values np times. So np in this case, our case is 6. So it will define NAND 6 times, right. So, similarly offspring objective, right. So, this variable is going to be used to save the fitness function of the offspring, right. So, OF offspring, this OBJ indicates that it is the fitness function value or the objective function value. So, this is offspring OBJ, right. Line 27 will determine the length of the lower bound or the number of decision variables, right. So, this P as usual helped us to determine the population. So, this population is between the lower and upper bounds, right, between 0 to 10 in this case. Okay. So, this line 31 to 33 is similar, right. So, it will determine the fitness function of each of these values, right. So, every time it will determine the fitness function of each solution, right. So, now we are in the iteration loop, right. So, for t is equal to 1, this loop will run for t is equal to 1 for now, right, and we are only sending the fitness function value. So, f indicates the fitness function value and np indicates the number of population, right. We are not actually sending the variable p which actually contains the population, right. The actual solutions are not required in tournament selection, only the fitness functions are required, right. So, that is why when we receive, we will not receive the solutions themselves for mating pool, we will only receive the indexes of the solutions which constitute the mating pool, right. So, now if we give step in over here, so over here we have this f, those 6 values and np as 6, right. So, now initially we are defining mating pool as a vector, right. So, this we require 6 members. So, that is why the size of mating pool is 6 by 1, right. So, this np is now 6, right. So, INDX as expected, it is giving a permutation of the 6 values from 1 to 6, right. So, right now it has given 1, 3, 6, 2, 4 and 5, right. So, that is in this variable 1 INDX, right. So, now the first competition is going to be between 1 and 3, the next competition is between 3 and 6, the third competition is between 6 and 2, the fourth competition is between 2 and 4, the fifth competition will be between 4 and 5 and the last competition will be between 5 and 1, right. That is how we are going to conduct 6 competitions, right. So, here for I is equal to 1 to np minus 1, right. So, if we execute this, so here we are selecting the ith value of INDX and the I plus 1th value. So, now I is equal to 1, right. So, basically we are selecting this 1 and 3, right. So, if we see candidate, it has to be 1 and 3. So, these two are the candidates, right, the first solution and the third solution, but what we are interested is in the fitness of these two solutions. So, in this line 9 will give that, right. So, step over here. So, fitness function if we see, it was 23.1937, 38.4169, 39.1922, right. So, but we are interested in these two fitness because we are conducting a competition between the first solution whose fitness function is 23 and the third solution whose fitness function is 39.1922, right. So, between these two functions we will find out which one is minimum, right. So, the minimum is the first one, right. So, that is why the value of ind is 1. Now, what we are doing is we are extracting the index of the solution located at 1. In this case it happens to be 1 itself, right. So, if we step, right. So, mating pool is 1, right. So, there was a competition between the first member and the third member and the first member won, that is why it is 1 over here, right. This 1 is not because this is the first location, this 1 is because there was a competition between the first solution and the third solution and the solution won, that is why we have 1 over here, right. Next time if we go over here, so index was 136, right. So, now we have done with the competition between 1 and 3, now we will be doing between 3 and 6, right. If we do this, so the candidates for the tournament is 3 and 6, right. So, now we need to extract the fitness function. So, the fitness function is given over here. So, what we are expecting candidate OBJ to have is 39.19 and 38.91, right. So, let us see, right. So, that those are the two values which we wanted, right. So, now among these two the second one is the minimum, right. So, what we expect in this to be 2, right. So, in this 2. So, now we need to see which solution corresponds to this winner, right. So, that can be obtained by candidate of ind, right. So candidate was 3 and 6, right. So the second one, so 6 is actually the winner. Remember, it is not IND is not the winner, IND only indicates the location of the winner. So at the position 2, it is the candidate 6, right. So the winner is 6 in this tournament. So mating pool will populate it with 6, right. So similarly we can conduct the third tournament, right. So it would be straightforward. So now the tournament is between 6 and 2, these are their fitness function values, right. So the solution located at the second position, right, in this case it happens to be the second solution itself is the winner, right. So in the third competition the solution 2, so if we keep doing this, in the fourth competition the solution 4, right, in the fifth competition it is again the solution located at fourth position, right. So this thing, so here if we see 1, 6, 2, 4, 4, right, these are the winners in the 5 competition, right, and this for loop is now over because this for loop was running between 1 and NP minus 1, 1 and NP minus 1, because if we had run till NP, this would have created a problem. We would have been accessing the NP plus 1th value, right. Since we do not have that value, we need to compete with the first one. We have written that exactly this portion is repeated over here, except for that the last competition is between the last member in INDX and the first member of INDX, right. So remember in the slide which I had written that the last competition is between the last member of the index and the first member of index, right. So in this case that happens to be 5 and 1, right. So that is because index, if we see, so the first competition was between 1 3, the second competition 3 6, the third competition 6 2, the fourth competition 2 4, the fifth competition between 4 and 5, except for solution 1 and 5 everyone has participated twice, right. So the last competition is between the solution 5 and the solution 1, right. So that is why we have this candidate 5 and 1. So if we step in this, so we get this, these are the objective functions. So the winner will be 23. So it is located at the second position, the winner is located at the second position. So this value 1 has to enter the mating pool, right. So this is our mating pool, right. So here if we look at the fitness function, this is something which we have done while learning genetic algorithm, right. So the best fitness function value here is 23.1937, which is the first solution, right. So and as we discussed, the best solution will appear twice, will definitely appear twice, right. So one is appearing over here, one is appearing over here. Similarly the worst solution was, if we look at F, the worst solution is located at the fifth position, right, 56.2516, and if we see fifth solution does not find a place in the mating pool, right. This is as expected because it does not matter with whom the worst solution competes, it is going to always lose, right. If it is going to lose in the tournament, it is not going to find a position in the mating pool. So in this case it happens that the fourth solution, right, which is 26.0702 occurs twice, right. As you can see, mating pool is not the solution at itself, it merely tells that the first solution, the sixth solution, the second solution, the fourth solution, the fourth solution and the first solution constitute the mating pool, right. So this only helps us to determine the indexes, right, of the solutions which are better, right. So now if we go into step, it goes into our main script, right. So now we have finished determining the mating pool, right. Now we need to access the corresponding solutions, right, because for a tournament selection we need only the fitness function value, we do not require the solutions as such, right, whereas for crossover and mutation we require the actual solution, right. So now if we execute this, so this parent, if we see, these are the solutions, so these are the solutions which will undergo crossover, right. So the first solution is repeated twice, right, it is over here and here, that is why it is at the first and the last location. The sixth solution was 3.3033, so it is located in the second position, right. So that is how we have found the parents now, right. Now the parents have been determined, we need to perform the crossover, right. So for crossover we are sending the parents the crossover probability 0.8, the distribution index 20, the lower bound 0 and the upper bound 10, right. Let us just step into this, right. So, first we are determining the number of rows and the number of columns of parent, right, and then we are randomly arranging it. So, now the solutions have been shuffled, right, 4, 2, 6, 5, 3, 1. Since we have shuffled with RandPerm, the solutions can be considered to be randomly arranged, right. So, we will perform a crossover between 4 and 2, 6 and 5 and 3 and 1, right. So, there will be 3 crossovers because we have 6 solutions. So, the number of crossover is NP by 2 times, and each time we will get 2 offspring. So, the total offsprings will be still NP. So, now we have arranged the parents, the parent solution as per this index, right. Initially the parents were arranged like this, right. Now we have shuffled using this INDX, right. So, the first solution is 4.3599, 2.0465, which is over here, right. So, we have randomly shuffled the solutions, right. To store offsprings, we create this 6 by 2 matrix with NaN values, right. 6 by 2 because there are going to be 6 offspring, the number of offspring will be equal to the population size and the number of decision variables will govern the number of columns. Right. So, now let us step into this. So, now I is equal to 1, right. In this case we first need to generate a random number, right. So, the random number which has been generated is 0.12, right, and the crossover probability is 0.8. So, since R is less than crossover probability, we will perform the crossover over here, right. So, if we step into this, so for j is equal to 1 to d, so for the first variable we will generate a random number. So, the random number happens to be 5967. So, it will not go into line 19, it will instead go to line 21, right. So, the value of beta is calculated to be 1.0103, right. Once we have calculated beta, we need to calculate the offspring, right. So, if we say I is now 1, j is also 1, right. So, we are using the value 4.3532 with 3.033, right. So, that if we access this over here, parent of I comma j and parent of I plus 1 comma j. So, those are the two values which will be participating in this equation to get us the offspring, right. So, here if we see, this value is found out to be 4.3586, right, and similarly for the second offspring also the first variable can be determined using this equation, right. So, so the second offspring, the first variable has been determined, right. So, this has to be repeated once more so that the second variable is also determined, right. So, at the end of this I is equal to 1, right, we have generated 2 offsprings. So, now we need to check whether this is in bounds or not. So, in this case it happens that it is in bounds. So, the next 2 steps will not have any impact on them, right, and then we go on to the next crossover, right. So, I is equal to 3. We have skipped 2 because these 2 solutions participated in the crossover, right. So, 4 and 2 have already participated in the crossover, now it is these 2 solutions, right. So, that is why we are skipping by 2. So, now I is equal to 3. So, if we generate a random number, the random number happens to be 0.1069. So, again we will have to perform the crossover, right. So, both the values would be generated. So, we have completed 2 crossover and we have got 4 offspring, right. Let us see the last one whether it goes into this crossover or not. So, the random number is 0.4678. So, again it will go into this crossover operation, right. So, this we can just quickly complete. Okay. So, here one thing that you need to remember is that we are generating 2 offsprings, right. So, offspring I as well as offspring I plus 1. So, both of them need to be bounded. So, here if you see in line 28, 29 what we are doing is we are bounding for both the solution, the ith offspring and the I plus 1th offspring. We are checking for the lower bound, right. So, the offspring is indicated by offspring I comma colon. So, this the highlighted portion indicates the offspring, this is the lower bound and we are using the max operator. So, what we will get over here in line 28 is that the ith offspring no longer violates the lower bound after this line is executed. Similarly, this line 29 is for making sure that the I plus 1th offspring does not violate the lower bound, right. So, both of these lines only take care about the lower bound, and similarly both of these lines, line 30 and line 31 take care about the upper bound, right. So, the ith offspring we are using the min function to make sure that it does not violate the upper bound, and similarly in line 31 we are bounding the I plus 1th offspring with the upper bound. So, this you need to make sure that both the solutions do not violate the upper and lower bound, right. So, that is why we have 4 lines over here. So, at the end of crossover we have this as our offspring, right. So, the offspring have been generated. Now, these offspring have to be mutated, right. So, this is sent into the function mutation poly, right. So, if we step in over here, again we determine the number of rows and the number of columns which constitute the population size and the number of decision variable. So, each member has to undergo mutation. So, we have this 1 to NP, we generate a random number, in this case it happens to be 0.4831 and our mutation probability is 0.2. So, this condition is not satisfied, right. So, it will not change anything, right. So, the first offspring will remain as such, right. So, this solution will remain as such, right. So, the second time we generate a random number which is again 0.5052. So, it will again not satisfy this condition, right. So, no change in the offspring, no mutation is happening. So, the third time random number is generated is 0.3, again no mutation, right. The fourth time 0.79, so again no mutation is happening, right. So, the fifth time it is 0.58, so no mutation, right, and this time it is 0.1623, right. So, since it is less than PM, we will have a mutation occurring over here, right. So, it satisfies this condition, so it has come into this loop. So, for every variable we need to generate a random number. So, the random number generated now is 0.7008. So, since that is greater than this 0.5, we will be using this equation to calculate the delta. So, since it is for the 6th solution, I is equal to 6, right. So, for I is equal to 6, if we see the solution initially was 4.2732 and that has changed to 3.8480, right. That is because of the mutation, that particular variable has been mutated so far, right. So, if we continue this, right, this is for the second variable, right, we determine delta, again if we see look at the offspring. So, 2.0137 has been changed to 1.9787. So, in this case it happens that all of the variables are within the bounds. So, these two statements will not have any effect, but if it had been out of the bounds, these two statements would have helped us to bring it into the bounds. So, if we complete this, right. So, now we have generated offspring from the mutation, right. So, we have this offspring which is within the bounds. So, we need to calculate the fitness function of this, right. So, here we are determining the fitness function of the offsprings. So, now we have the population P, right, and the offspring. So, offspring is 6 rows 2 columns and P was already the initial population, right. So, that was also 6 row 2 columns. So, if we combine them, right. So, now we will have combined population which has 12 rows, right, and 2 columns. So, this top one is the parent or the variable P and the bottom 6 are the offspring, right. So, now what we will have to do is we will combine the objective function and the sort, right. So, this within this square brackets we are stacking the objective function similar to the way we stack the solutions and we are sorting it. So, this indicates that the 12th solution is actually the best solution 18.7224. So, that corresponds to this particular solution, and the next best solution is the first solution, the third best is 9, the fourth best is 10 and so on, right. So, these are the fitness function. Now, we need to appropriately extract that solution, right. So, 18.7224 is here, which the solution corresponding to this, that is 3.8480 and 1.9787. So, we need to extract that particular solution. So, before extracting, right, we are just reducing the f to the first NP elements, right. So, NP is no longer 12, right, it is just the first 6 better solution, right. So, this first 6 better solution are taken and the rest of the values are discarded, right, these 6 values are discarded. Similarly, from this combined population we are extracting the NP best members, right. So, when we do ind of n 1 to NP, it will actually correspond to 1, 2, 3, 4, 5, 6, these 6 solutions. So, we will extract these 6 solutions from the combined population and store it in the variable p, right. So, p is now again 6. That completes one iteration of genetic algorithm, right. So, this we can implement it multiple times. So, in this case let me just continue so that it will complete everything. So, here we had taken only 10 iterations, right. So, at the end of 10 iteration the best fitness function value we obtained is 1.6885 and the solution corresponding to it was 1.2505 and 0.3532, right. So, f also if we see the first value will be 1.6885 and if we look at this p, the first value will be the same 1.2505, 0.3532. So, this happens only in genetic algorithm because here we actually sort the population. Rest of the meta heuristic techniques which we discussed, we never sorted the fitness function value, right. So, that is why the best solution could be located anywhere and we were using the min function to identify where it is located and what is its location and we were extracting the corresponding solution. Over here it is always guaranteed because we are employing a mu plus lambda strategy, it is always guaranteed that the first solution would be the best solution, right. At the end of iterations, all the iterations, the first solution will definitely correspond to the best solutions. So, that completes the implementation of genetic algorithm, right. So, when compared to the rest of the meta heuristic techniques, it might seem slightly tricky to implement, right, but once you look into the code couple of times it will become much easier for you to understand the code and the functioning of genetic algorithm, right. As we have discussed multiple times, these meta heuristic techniques are useful only if we are able to do a large number of iterations with a larger population size fairly quickly, right, and since these are stochastic techniques we need to again run it multiple times. Right. So, it is just not possible to use these techniques using pen and paper, right. So, we need to have an automated way and that is best implemented using programming language. So, in this case we had taken it as MATLAB. We will also circulate the codes which we have developed, right. So, you can actually look into the codes in the debug mode and try to further understand. Right. As usual, if you have any doubts you can drop an email, we will get back to you. That is the end of this session. In the next session we will be looking into artificial bee colony optimization and its implementation using MATLAB. Thank you.